Hello, can you hear me? Hello, can you hear me?
Yeah, I can hear you.
Yeah, okay. So we'll continue with number theory. We
I
had,
thought we were supposed to do geometry this class. I haven't done the number theory. I did geometry.
we'll do geometry in the next class.
Oh, but
Uh,
I haven't done the number theory.
I had given you four problems, no?
I haven't done them yet because I was sick, so I just did some of the geometry problems.
We'll do it in
Because,
class.
okay. Oh,
The
what were the
first,
problems again?
did you write them down?
Yeah, I did, but I think I lost the paper, like
How
right
would
now.
you
Because
have,
I have the number theory in like a separate notebook, so I think that one's somewhere else. Like I don't have it right now. I have the geometry because I thought today's class was geometry.
find the sum of the digits in the decimal representation of the number. This is the first question. You have to find the sum of the digits in the decimal representation of this number. The number is 5 to the power 2010 and 16 to the power 502.
Okay.
This number right now is not in its prime factorization. You should convert it to 2 power something.
Yeah. So it'd be 5 to the power 2010 times 2 to the power of 2008.
Right.
Yeah.
So what happens when you get 1 5 and 1 2 together? Comes
It
a
be
10, right?
yeah.
So notice here that obviously the powers are 2008 and 2010. So you can write it as 5 into 2 to the
Yeah.
power 2008. And then you what will be left over will be 5 square.
Right.
Clearly, this number will become 25. times, and this is 10 to the power 2008, right?
Yes.
So that means there will be 2008 zeros after this.
Right.
The number will be something like this 25,000 goes on till 2008 zeros.
Yeah.
So it is very easy to find the sum of the digits in this number because all the other digits are zero,
Right. So then the sum is just 7.
right? The sum of digits becomes 7. So that is the first one. It is
Okay.
pretty easy if you do the prime factorization.
Yeah.
Question 2 was if n is a natural number, it's a natural number where n square is equal to 25 to the power 64 times 64 to the power 25. Again, you have to find the sum of the digits of n.
Okay. So you have that it's 5 to the power 128 times 2 to the power of 150. Then you can combine that to get that n squared equals 10 to the power of 128 times 2 to the power of uh
22.
yeah, 22. And then because you can square root it, you get that n is equal to 2 to the power 11 times 10 to the power 64. And then 2 to the power 11 is uh
2 to the power 10 is 1024.
yeah, so then 2 to the power 11 is 2048. So then the sum is uh 14.
So it is also a number that is followed by a lot of zeros. So all you need is these, right?
Yeah.
So sum of the digits becomes 14. So
Yes.
in these both of the first and second problems, it's all about just doing the prime factors.
Yeah.
And after that, it is easy. The third problem is about a different thing. Now, here we have to find the greatest positive integer, all of whose digits are distinct, all of whose digits are distinct, and no two adjacent digits, no two adjacent digits are consecutive integers. Consecutive integers. So you cannot have a situation like 7, 6, 5, and all.
Yeah.
And all the digits must be different, right?
Right.
It cannot be like this also. 9, 7. You cannot put 8 here now.
Because that's consecutive.
Right.
Yeah.
So you have to find the largest positive integer which satisfies these conditions.
Okay.
First thing to realize, if you have two natural numbers, m and n, two natural numbers, m and n, and let's say they have different number of digits, then the one which has more digits is larger, right?
Yeah.
More digits is larger, and in case they have same number of digits, if they have same number of digits, then if you want to figure out which one is larger, what you have to do is choose the highest digit where they are different, right?
Right.
That's how we compare two numbers which have same number of digits. 9, 8, 7, 4 versus 9, 8, 6, 3. We
Yeah.
choose the highest digit which is not the same.
Mm-hmm.
And whichever one has a highest digit which is not the same, this one is going to be larger.
Right.
So in order to figure out the biggest possible number, you need to be able to compare two numbers and figure out which is larger. So these are the two rules that you need to keep in mind. If they have same number of digits and if they have different number of digits, how we build which one will be larger.
Right.
So now one way to here you have to find the greatest positive integer. So one way to think about it is to just try to build that number, make the largest possible number which satisfies the requirements of the problem, right?
Right.
So obviously we should start with which digit?
9.
You start with 9, then the next number after that cannot be 8.
Right.
So what should it be then?
7.
Okay, next number after that cannot be what?
It can't be 6 or 8, so it has to be 5.
Hmm. Okay, so after that, what is the next number after that?
8.
Right. We are putting 8 because now there is no consecutive stuff, and this is the largest digit that is available.
Yeah. And then
After,
6.
hmm,
And then 4.
hmm,
2.
hmm.
But then 1 and 3 don't make sense because they're consecutive.
Right. So after that, what? 0.
0. Then
And
3 and 1.
3 is after this, and after this, you can put 1. But
Yeah.
after that, you cannot put any other number because after that, as soon as you put anything, it repeats at least once.
Yeah.
We have used up all the digits.
Mm-hmm.
So all the digits have to be distinct. So now we have to stop here, right?
Right.
The method that we have just now used to make the number is called a greedy algorithm. Why is it called a greedy algorithm? Because we are trying to satisfy the condition immediately everywhere, every
Yeah.
time. We are not going for some grand method or long-term strategy. We are directly trying to fit all the conditions and make the number every step, making it as big as possible, right?
Right.
That's the number. That's the answer. Do you understand what we have done?
Yes.
Okay. The fourth problem was find the least positive integer whose product of digits is 10 factorial, where I hope you know the meaning of factorial symbol,
Yeah.
right? So it is a
Yes.
product of numbers from n to 1 if it is n factorial.
Yes.
So we have to find here the least positive number whose digits can be multiplied and you get 10 factorial.
Mm-hmm.
Try it out.
Well, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can rewrite like 3 times 2 times 1 as 6. And then you can rewrite 10 as 5 times 2. So then you could write a number like 2, 4, 5, 5, 6, 6, 7, 8, 9. And that would
Right
multiply.
now, we have to find the least number.
Oh, least number.
We don't have to find any random number. Product of the digits is not the only thing. We have to find the smallest such number.
Right.
In order to find out the smallest number, you have to think about the how many least number of digits can you make it happen. So in order to realize that, you will need to find the prime factorization of this. This is the product of 10 numbers, but you can write it as powers of 2, 3, 5, 7, and all, right?
Right.
Why are we looking at that? Because when I make my number n, I want to have the least number of digits possible, right?
Yeah.
So I have to make sure that when I make my n, it will have the same product as this.
Yeah.
So for that, to make sure of that, you need to find out how many powers of 2 are there, how many powers of 3 are there, and so on, right?
Yes.
So 2 powers will be from here there is 1, from here there is 2, so total 3. From here you get another 2, so you get 4 powers of 2. Then you get 3 powers from here, so 7, and 1 from here, so it is 2 power 8, right?
Yes.
And 3 power is from here 1, from here 1 more, from here 2 more, right?
Mm-hmm.
So 1, 1, and 2, so 3 power 4, and it is 5 power 2, correct?
Yeah.
And it is 7 power 1, right?
Yes.
So in terms of prime numbers, this is my prime factorization of 10 factorial.
Mm-hmm.
I need to make up the digits in such a way that the product of the digits is equal to this number, and I want to
Right.
keep the number of digits as small as possible, right?
Yeah.
Now you have to think of that thing, like how to make the number of digits as low as possible.
Well, you could rewrite 2 to the power 8 as like 8, like
Hmm.
8, 8.
Right. So that is
Mhm.
basically one way to reduce digits is keep 2 cube as 8.
Yeah.
That will be a single digit, right?
Mm-hmm.
Instead of having two multiple places. But
Right.
you should not start by looking at these digits. You should start by looking at the higher powers, like 5 and 7 prime numbers. Is
Yeah.
there some way to have 5? You can't do 5 square 25 as a digit,
No.
right?
No.
So there is nothing you can do about 5 and 7, right?
Yeah.
So they have to be present. So 5, 5, and 7 have to be there, right?
Yeah.
Three digits are guaranteed, right?
Yes.
After that, you should think of now how to handle the 2 power 8 into 3 power 4, right?
Right.
One way to reduce it is take as many powers of 2 in a single digit as possible. So you got the idea that we should use 8s, right?
Yeah.
We can use 8 two times
Right.
and we'll be left with 2 square, right?
Mm-hmm.
And here we can use 9, 3 square, right?
Yeah.
So 9 is 3 square. Uh, so you can either do two nines, correct?
Correct.
That will completely handle all the 3 power 4.
Mm-hmm.
Or you could do, or you could have one 9 and one 3 you can combine with this, right? The remaining.
Yeah.
So there are some possibilities here for us. So far what I know is 5 is present, 5 is present, 7 is present, right?
Yeah.
So total number of 8s can be maximum is 2, right?
Right.
So what we can do is um, okay, so what is the number left? So we are going to put two 8s anyway. That will reduce our problem because two 8s, if we put 2 power 6 is already gone, right?
Yeah.
After that, what is left is 2 square and 3 power 4, right?
Right.
And there are different possibilities for this because one way to do it would be to take two nines and one four, right? 994, see? Correct?
Right. Yeah.
And another way to do it would be to take one single 9. So that means 3 square is gone. So now we are left with 2 square and 3 square. So then you will do two sixes, right?
Yeah.
Do you understand what I'm saying?
Yeah, I understand.
So what I have done is used up the 5 square 7. You have reused these three digits. And then 2 power 6 we have taken in 8 and 8, right? And
Yeah.
then the remaining part we can use three digits to make, right?
Yeah.
So the choices are now we have to make the least possible digits,
Mm-hmm.
least possible number using these,
Right.
right?
Yeah.
So it is possible for us to make that. We'll start off with the lowest number. So let's do case one where we are doing this, right? So
Mm-hmm.
we'll start off with 4, 5, 5. then there is 7, then there is 8, 8, and then 9, 9, right?
Right.
That is one number. And from here, the number that we end up getting is obviously 5, 5, 6, 6, 7, 8, 8, 9.
Yeah.
Notice that both of them have same number of digits, 8 digits, but obviously this is smaller. Do you understand what I'm saying?
Yeah.
The smaller number is the one where we use 2 9s and 1 4, not the one where we use 9 and 6 and 6.
Yep.
The point is that we have used the 4 and the beginning here rather than the 5 and all, right?
Yeah.
So now we are satisfying everything we needed. We got product of the digits is 10 factorial and we also made it as small as possible. Right?
Yeah.
Okay. The next question was this. What is the greatest n? What is the greatest n such that the digits of the number n factorial minus n are all different? The number should have a value of n factorial minus n. However, it should always have different digits. And what is the biggest possible number like that? Okay.
Yeah.
You have 5 minutes. Think about it. I will give you some information here to make your job easier. So, for example, I will give you what is 10 factorial minus 10. The value is 3628790. 11 factorial minus 11 is equal to 399,16789. And 12 factorial minus 12 is equal to 47,900,1588. This is equal to and similarly 14 factorial minus 14 is this. So, assume that the question has given you this information just so that you don't have to multiply. But the question is still the same. You have to find the greatest n such that the digits of n factorial minus n are all different.
Okay.
Do you think these numbers are satisfying the conditions of the problem?
No, because they have the repeating numbers.
Right. So we can see that for n is equal to 11, 12, 13, and 14, the digits are repeating.
Yeah.
For this, it was not repeating, right? So looking at it, it looks like n is equal to 10 satisfies the conditions, right?
Yeah.
But you have to see if n is equal to 10 satisfies the conditions, you don't need to look for n is equal to 9, 8, 7 and all, right?
Yeah.
But we still have to think of a reason why maybe there is a higher power that doesn't, right?
Mm-hmm.
So the question is now over if you can prove that for n greater than 14 also, it will not work. It won't satisfy the conditions. So basically, you have to prove that somehow. Do you understand what I'm saying?
Yeah.
The digits should repeat there somehow.
Yes.
The point is to think about the number of digits in your n factorial minus n. Because if the number of digits in n factorial minus n is greater than or equal to 11, then can you have 11 different digits?
Oh, no. No, you can't.
So you can see here that number of digits was here 3, 3, 6, 4, 10, right?
Yeah.
And here it was 11, so it is guaranteed to have repetition, right?
Right. Okay. Yeah.
And how would you prove that if you have, let's say, 15 factorial minus 15 or 17 factorial minus 17, it will have more than 11 digits?
Because it's a greater number.
It is greater, and if you didn't know this, right, you can
Yeah.
still prove that because if you compare 14 factorial with 10 power 10, right, you can do the prime factorization and realize that 14 factorial itself is much bigger than this.
Yeah.
By doing the 2 powers and 5 powers and all, we can figure that out, right?
Yeah.
So if your 15 factorial minus 15 has a prime factorization that tells us that it is 10 power 11 or something, it cannot have less than 10 digits then, right?
Yeah.
So we can at least compare the prime factorization of 15 factorial to get an estimate of how many digits it will have, right?
Mm-hmm.
Do you understand what I'm saying?
Yes.
And we have to compare it with 10 power 11, 10 power 10 to know how many digits they will have.
Right.
And if you know that the number of digits is more than 10, automatically then there will be repetition. So anything above 14 and all won't work, right?
Right.
So the largest n for which it works is then just 10, right?
Right. Yeah.
So that becomes the answer then. So here some calculation is required. That's why I gave you these values. But the idea is look for the number of digits, find at least one n which fits the condition, and after that think of the higher ones, right?
Yeah.
Okay, the next two problems are similar, so I'll give them together and you need to try them. Problem 6 is, you know what a perfect square is, right?
Yes.
Find three distinct non-zero perfect squares whose sum is also a perfect square. Sum is also a perfect square. So that is the first one. And the second one is, find a natural number n, natural number capital N, such that n minus 76 and n plus 76 are both perfect cubes. You understand, no?
Yes.
So try these two. You have 5 to 10 minutes. You found anything for sixth one?
I haven't found anything for 6, but I did 7.
How?
Um, so I just listed out some perfect cubes that I know, like 1, 8, 27, 64, 125, 216, and 343. And then 76 times 2 is 152. So we know that the perfect cubes have to be 152 apart.
Mm-hmm.
And then 216 and 64 are 152 apart. So then n is 140 because it's in between. 76 in between.
Okay, that is correct. But ideally, what we should do is, in case we have to find more of these, what we have to really do is find a situation where the difference of two cubes is 152, right?
Yeah.
So if you call this as x and this is y, we need y, this is x cube and this is y cube rather. You need y cube minus x cube to be 152.
Yeah.
So how can we solve this in a better way? So what we can do is we can find y minus x factorization of this. What is the other factor?
Uh, y squared plus xy plus x
Hmm.
squared.
So this is equal to 152. Now, if we want this to happen, then basically we know that y minus x is a divisor of 152.
Yeah.
Okay, fine. So also we can say that y square plus xy plus x square can be written as is equal to y minus x whole square plus 3xy, right?
Yeah.
That is obvious. So we can also say that y square plus xy plus x square is greater than equal to y minus x whole square,
Right.
right? Because it is y minus x whole square plus 3xy, right?
Yes.
So the product here is such that you can say the product of y minus x and y square minus xy plus x square
Mm-hmm.
is greater than equal to y minus x into y minus x whole square, right?
Yeah.
So this is greater than equal to y minus x whole cube, right?
Mm-hmm. Yes.
So we are getting 152, which was equal to this, is greater than equal to y minus x whole cube,
Yes.
right?
Yeah.
Okay. Now that easily tells us that obviously y minus x cannot be 6.
Yeah.
So we know that y minus x is less than 6,
Mm-hmm.
right?
Yes.
Okay, great. Now we also know y minus x is a divisor of 152.
Mm-hmm.
So the divisors of 152 will be what? The lowest divisors are 1, then 2, then 4 also, right?
Yeah.
After that, it will be above 6, right?
Yes.
So the options for y minus x will be only 1, 2, or 4, right?
Yeah.
Because it has to be less than 6 and it has to be a divisor of this.
Right.
So now we just know that we can check these three cases now. We can say y minus x is equal to 1 is one case, y minus
Mm-hmm.
x is equal to 2, and y minus x is equal to 4, right?
Yes.
So how do I check these cases? What I will do is I'll take y is equal to x plus 1 for first case, right? Correct?
Yeah.
So if y minus x is equal to 1, we immediately get this equation is equal to 152, right?
Yes.
We start from here. We have y square plus xy plus x square is 152, and we are doing case 1 where y minus x is equal to 1, which implies y square plus xy plus x square is equal to 152, and If you put y is equal to x plus 1 back in this, you will get x plus 1 whole square plus x into x plus 1 plus x square.
Yeah.
And you end up with a quadratic equation like this: 3x square plus 3x minus 151 is 0,
Yeah.
where we don't have any integer solutions. Don't have any integer solutions. You can check the roots, they're not integers.
Yes.
We needed integer solutions. So then we'll go to case 2, where y minus x is equal to 2, right? And then we will get the equation would become y square plus xy plus x square is equal to 76, right?
Yes.
Because we are putting 2 here, right?
Mm-hmm.
And then here we'll put y is equal to x plus 2 and make a quadratic in x now, right?
Yes.
So we'll get x plus 2 whole square plus x plus 2 into x plus x square is 76. And if you make the quadratic after simplification, it becomes x square plus 2x minus 24.
Right.
And from here you get x is equal to 4 or minus 6. And we wanted positive numbers, so we'll take x is equal to 4, right?
Mm-hmm. Right.
And if you do x is equal to 4, your y is equal to 6. And the cubes are basically 64 and 216 that you found.
Yep.
So your n is in between and n will be 140. The reason
Yeah.
we are doing this like this is because in harder problems, it will be difficult to get the number directly. It's not going to be so easy. So
Right.
what we are trying to understand is how do we approach a situation where we need to find x and y where something like this was given. So
Mm-hmm.
what was the general thing we did? We factorized it, right?
Yes.
We factorized it like this. And then from here we said y minus x is a divisor of 152, right?
Right.
That is one fact. Then the second thing we did was we wrote y square plus xy plus x square as y minus x whole square plus 3xy. So it is clearly greater than y minus x whole square. So if you use that in this equation, you get 152 is greater than y minus x whole cube.
Right.
And from there we got y minus x is less than 6.
Yeah.
And then combining this with this, the only options for y minus x became 1, 2, and 4, right? It has to be a divisor and it has to be smaller than 6. If you check the case y minus x is equal to 1 or equal to 4, there is no integer solution in those cases. The solutions are only there for the third middle case where y minus x is equal to 2. Do you understand what we have done?
Yes.
So such logic or such steps will be common in number theory as we go for harder problems. So you need to understand what we have done here. Okay. Then for the sixth one, we need 3 squares such that the sum of them is also a perfect square, right?
Right.
So first thing you should do is list down some squares. If you list down all the first few squares, you can then start to see how we'll get that pattern happening. So these are the first few squares. You should think of combining 3 of them and seeing what is coming, right?
Mm-hmm. Right.
So you can easily see that 4 plus 9 plus 36 is what?
Uh.
49.
Right.
So these are the sum of three squares is also a square, right?
Oh, right.
So the smallest numbers for which this happens are 2, 3, and 6, whose squares add up to 7 square,
Right.
right? So
Yes.
it is very easy to spot a pattern, but you'll only spot it if you write down some squares like this.
Yes.
You can keep adding and see, you'll be able to find some more also if you want. But ultimately, like you'll have to use at some stage here a Pythagorean triplet. You should know, for example, that 5 square plus 12 square is 13 square, right? We know this
Yeah.
from Pythagorean triplets. And we can also write 5 square as what? 3 square plus 4 square.
Right. Yeah.
So then we get 3 square plus 4 square plus 12 square is equal to 13 square.
Yes.
So a general method would be to get Pythagorean triplets and take one of them, and hopefully that is also a Pythagorean number,
Mm-hmm.
right?
Right.
In general, there are many such numbers which satisfy this property that sum of three perfect squares is also a perfect square. And you can find all of them using this identity. For example, if you do 1 plus 2n square whole square, what is the square of this? It will be 1 plus 4n power 4 plus 4n square, right?
Yes.
So this is 1 square plus 2n square square plus 2n square, right?
Yep.
So we can clearly see that the sum of the squares of these numbers is equal to the is equal to the square of this number,
Right.
right? Anytime you take any n, now you can make up any infinite number of such examples now, right?
Mm-hmm.
Do you understand what I'm saying right now?
Yes.
Anytime you put n is equal to 2, 3, 4, whatever, you can make up as many examples as possible because this is an identity. We are just doing perfect square of this, right?
Right.
So that is something that helps us get an infinite set of answers. We already found some small numbers for which it is working, right?
Yes.
Okay. Now I'll give you some problems. You need to write them down, and these are the ones that we'll start off our discussion in the next to next class.
Okay.
So problem 8, we have done 7. Problem 8 is find a natural number n greater than 1000 such that n is simultaneously a perfect square and a perfect cube and a perfect cube. That is problem 8. Problem 9 is if 1 by 1 plus 2 plus 1 by 1 plus 2 plus 3 plus so on till 1 by 1 plus 2 till 20 is equal to m by n, where m and n are positive integers with no common divisors other than 1. Divisors other than 1. You have to find out m plus n. These are problem 8 and 9. I will give you a few more. Problem 10 is find the number of different quadruples A, B, C, D. Basically, number of different combinations of four numbers A, B, C, D of positive integers such that AB is equal to CD is equal to A plus B plus C plus D minus 3. Write down these three questions. Tell me when
Yeah.
you've written them.
Yeah, I've written them.
Okay. Problem 11 then is solve in positive integers the equation 1 by x plus 1 by y is equal to 1 by 7. You need your answers to be positive integers. Then problem 12 is prove that if the number A, B, C is divisible by 37, then the sum of the numbers BCA and CAB is also divisible by 37. By the way, here, why am I putting a dash on top?
That means they're not multiplied, they're like written out side by side.
I'm putting a dash because what I mean is that these are digits.
Yeah.
Digits are A, B, and C, right?
Yes.
So technically this number is 10 square A plus 10 into B plus C.
Right.
This is like a number like 3, 2, 1 and all. It's not 3 into 2 into 1, A, B into B into C, right?
Yeah.
So you should know that. And one last problem. So you have written this 12th one. Prove that if the
Yes.
number ABC is divisible by 37, then sum of the numbers BCA and CAB is also divisible by 37.
Yeah.
Okay, so then problem 13 is prove that if the sum of the numbers AB again with a dash and CD is divisible by 9 then the number ABCD with a dash is also divisible by 9. So these 5-6 questions you should try out and we'll discuss these on Thursday. Okay.
Okay.
Tuesday's class will be for geometry.
Yep.
And in geometry, I think we have to do chapter 14 or the new chapter, which is on homothety and all. or
Yeah.
the transformations.
Mm-hmm.
So just read up that transformations chapter. We will look at that in Tuesday's class.
Okay.
Okay, fine. Try these questions. Don't lose the questions. Right?
Mm-hmm.
Now are you feeling better now?
Yeah, I'm feeling better. Thank you.
When is your school exams and all?
Oh, I think the final exams are like in April, May, something like that.
Okay. So right now this is your grade 9 exams, right?
Yes.
So this is like your first year of high school.
Mm-hmm. Right. Yeah.
And next year you're planning to take some physics as well, right?
Yeah, next year I'm planning to take AP Physics 1.
And in this AP Physics 1, are they calculus based or not calculus?
I don't know. I can send like this description of the course to you.
Right. So send the description because you need to. So there are multiple ways in which the courses are done. Some courses are calculus based and some are not. So
Oh, okay. Yeah,
so you need to find that out. And if it is not calculus based, it will be very trivial, very easy. So that will not be very difficult. But if it is calculus based, then we need to make some preparation for that.
okay.
Some
Yeah,
basic
I'll check it out.
calculus.
Yeah.
Okay.
I'll send you the summary of the course.
Right.
Yeah, okay. All right. Or like the course
Fine.
description. Yeah.
Yeah.
All right. Thank
Mm,
you.
Bye.
Bye.